Imagine placing two perfectly smooth, uncharged metal plates in empty space, parallel to each other. Intuition tells us that, since they carry no charge, they should feel no force between them. However, quantum physics tells a different, more bizarre story, one where an invisible force, seemingly from nowhere, gently pulls the plates together. This phenomenon, known as the Casimir Effect, was predicted in 1948 by Dutch physicist Hendrik Casimir. It challenges our very understanding of emptiness, showing us that even in a vacuum, where we assume there is nothing, there exists a restless sea of energy that shapes reality in unexpected ways. At first glance, the Casimir Effect might seem like an obscure curiosity of theoretical physics. However, it has far-reaching implications for nanotechnology, cosmology, and even futuristic propulsion concepts. This journey into the quantum vacuum will reveal how this force emerges, how scientists have measured it, and how it could shape the technologies of the future. For centuries, scientists thought of a vacuum as truly empty, a void devoid of matter, light, or any influence. This classical notion of nothingness dominated physics until the rise of quantum mechanics in the 20th century. Quantum mechanics radically changed this perspective. According to quantum field theory, a vacuum is not truly empty but instead teeming with invisible activity. The fabric of space itself is filled with quantum fluctuations, tiny bursts of energy where particles momentarily appear and disappear. These virtual particles, though fleeting, have real and measurable effects. Imagine the vacuum as a vast, invisible ocean. While it appears calm on the surface, beneath it, waves are constantly forming and vanishing. These waves represent the quantum fluctuations, short-lived virtual particles that pop in and out of existence. Normally, these fluctuations balance out, creating no noticeable effect. However, when boundaries are introduced, such as two metal plates in close proximity, something fascinating happens. The quantum fluctuations become unevenly distributed, leading to a force that pulls the plates together. When two metal plates are placed close together in a vacuum, they act as barriers that limit which quantum fluctuations can exist in the space between them. Outside the plates, all possible quantum fluctuations occur freely. Between the plates, only certain fluctuations can fit within the confined space. This creates an imbalance. There are more virtual particles and energy fluctuations outside the plates than between them. As a result, a net force emerges, pushing the plates inward. The Casimir force is incredibly weak at human scales, but it becomes significant at extremely small distances. For example, when two plates are just a few nanometers apart, a billionth of a meter, the force becomes strong enough to be measured in the laboratory. This effect is not limited to metal plates. It has been observed in various materials and experimental setups, proving that the quantum vacuum is an active, force-generating medium. The Casimir force is difficult to measure because it is incredibly small compared to everyday forces like gravity or electromagnetism. Early experiments faced challenges due to surface imperfections, contamination, and unwanted electromagnetic interactions. The first precise measurement of the Casimir effect was conducted in 1997 by physicist Steve Lamoureux at the University of Washington. Instead of using two parallel plates, which are difficult to align perfectly, he used a curved metal sphere placed near a flat metal plate. By carefully isolating the experiment from external influences and using a highly sensitive instrument called a torsion balance, Lamoureux successfully detected the Casimir force, confirming Casimir's original predictions with remarkable accuracy. Other experiments were also conducted. 1998, Mohideen and Roy used atomic force microscopy to detect the Casimir force at nanoscales. 2001, Chan et al. Demonstrated the effect in tiny mechanical systems, proving its impact on nanotechnology. 2009, Capasso et al. Showed that, under certain conditions, the Casimir force could be repulsive instead of attractive. These experiments cemented the Casimir effect as a real, measurable force, highlighting the tangible influence of quantum fluctuations. The Casimir effect finds application in the real world, but also creates substantial future potential. 1. Nanotechnology and microelectronics. At the microscopic level, the Casimir force plays a crucial role in nanotechnology and microelectromechanical systems, MEMS. Tiny devices, such as microscopic sensors and actuators, can experience unwanted adhesion due to the Casimir effect, leading to a phenomenon called stiction, where components become stuck together. Engineers are working on ways to counteract or harness the Casimir force to improve the reliability of nanoscale devices. 2. Dark energy and the expanding universe. The Casimir effect is closely related to vacuum energy, which has deep connections to dark energy, the mysterious force driving the accelerated expansion of the universe. Some physicists believe that understanding quantum vacuum energy could provide insights into why space itself expands at an accelerating rate. 3. Repulsive Casimir forces, a step toward quantum levitation. While the Casimir force is usually attractive, recent experiments have demonstrated conditions where it can be repulsive. This discovery opens the door to frictionless nanotechnology, where components can move without touching, potentially leading to quantum levitation and revolutionary materials. 4. Exotic propulsion concepts. Some speculative theories suggest that harnessing the Casimir effect could lead to vacuum energy propulsion systems. While this remains highly theoretical, the idea of tapping into quantum fluctuations to power spacecraft is an exciting prospect in advanced propulsion physics. The Casimir effect is a striking reminder that the universe is far more complex than it appears. Even in a perfect vacuum, where we expect nothing to exist, an invisible force emerges from the quantum fluctuations that permeate space. This phenomenon not only deepens our understanding of quantum field theory but also has tangible implications for technology, cosmology, and future scientific breakthroughs. From nanotechnology to the mysteries of dark energy, the Casimir effect offers a glimpse into the hidden forces shaping our reality. As we continue to explore the quantum vacuum, who knows what other secrets it holds? Could we one day harness vacuum energy for limitless power? Might we manipulate quantum forces to achieve new forms of propulsion? One thing is certain: the Casimir effect is not just a scientific curiosity, it is a gateway to the future of physics.